Hi, and welcome everyone to this week's One World Mind Seminar. It's my great pleasure to introduce our speaker, Dr. Joe Kileel, who is an assistant professor in the Department of Mathematics and the Odin Institute for Computational Engineering and Sciences at the University of Texas at Austin. Previously, Joe was a postdoctoral fellow at Princeton with the Simons collaboration on algorithms and geometry, and received his PhD in mathematics from the University of California, Berkeley. He has been funded various times by the NSF and the Department of Energy, and recently was awarded the J. Tinsley Oden Faculty Fellowship at UT Austin. His research broadly focuses on computational algebra and applied mathematics, with a special focus on applied algebraic geometry and 3D reconstruction in cryo-EM and computer vision. Today, we're pleased to have him talking on covering number of real algebraic varieties and applications to data science. Turn it over to you, Joe. Thanks.
Thanks a lot for that generous introduction and also the invitation to speak. Um, indeed, I'll be talking about covering number of real algebraic varieties and applications to data science. The talk is based primarily on one paper, and here's the arXiv indicator. The title is a bit of a mouthful, and I'll unpack it in the opening slides. Okay, so this is joint work with Yifan Zhang, my PhD student at UT Austin. Okay, background. So the talk is about covering numbers of some specific sets, but let me just back up and remind you what covering numbers are in general. So suppose you have some subset of a metric space. We'll think here about sets V in a Euclidean space, R to the capital N, or perhaps the complex numbers to the capital N. And then for any positive epsilon, you can talk about the epsilon covering number of V as the smallest number of balls, Euclidean balls, of radius epsilon with centers in V that are needed to cover the set V. Okay, so it's a simple basic concept, and here's a picture illustrating it. So suppose the set V is the interior of this bold curve, then I'm showing you here some covering by epsilon balls in the plane. And the minimum number of balls needed to cover this interior completely, that would be the covering number of V. Okay, this picture is not completely accurate because the center of this ball is actually outside of V, and in the definition, I wanted the centers to be in V. But okay, the idea is illustrated here. Okay, this is the definition again. So why is this sort of abstract metric space-like definition relevant to data science and applied math? I'll give you a few different reasons why it's important. One is that if you can bound the covering number of V, then you can bound volumes of so-called tubular neighborhoods of V. So a tubular neighborhood of V is, say, the delta tubular neighborhood of V is the thickening of V, where for every point in V, I replace it by a Euclidean ball of radius delta. This is like a thickened version of V. And it's often relevant to upper bound the volume of tubular neighborhoods of sets. An important example comes from numerical algorithms. When V represents the set of ill-posed inputs to some numerical algorithm, then the tubular neighborhood of V is the set of ill-conditioned inputs to the numerical algorithm. For example, suppose we're just considering inverting a square matrix. Then the set of ill-posed inputs V would be determinant zero matrices. And the tubular neighborhood of this would be highly ill-conditioned matrices. So it's sort of relevant to know how the volume of ill-conditioned inputs, and covering number gives you a way of tackling that. Okay, in approximation theory and dimension reduction, the covering number plays an important role. So, for example, if V is actually has a low intrinsic dimension, but is in a very high dimensional Euclidean space, we might like to apply a linear projection um, to V while preserving pairwise distances. So as in the Johnson-Lindenstrauss transform. But we'd like to do that maybe to the entire set V. So the covering number of V gives us a way of controlling the dimension that we can reduce down to. There's also applications to topological data analysis, um, which is about estimating the homology of some space given noisy samples from the space. So here the covering number gives information on the number of samples required to accurately see the topology. Okay, so that's the covering number part. What about the real algebraic geometry part of the title? So in this talk, real algebraic geometries are just zero sets of systems of polynomials. Um, so you can actually get a rich set, a rich class of sets this way, a highly rich class of sets. And I'm just showing you two examples of real algebraic surfaces in R3. A notable thing is that real algebraic varieties can actually include singularities. So they include some non-manifold structures as well. Okay, but just a very concrete object, just a system of polynomial equations and the simultaneous zeros. Okay, so here it is. This is a real algebraic variety. I have a variable x in capital N with capital N coordinates, and here's my system of polynomial equations, f1 through fm. So there should be an equal to 0 here at the end. Sorry about that. So these are all equal to 0. I'll consider these. I will also consider closely related class subsets that here I'm calling images of real polynomial maps. So in this top equation, V is presented as a zero set of some equations. There should be an equal to 0. Here, V is parameterized by polynomials. So there's some parameter variable y, which is in R little n, and V consists of all the tuples P1 of y up to P capital N of y. There's a polynomial parameterization here. This is not exactly the same as the real algebraic variety, but our methods will also let us control the covering number of these sets. And we'll see a lot of applications for these polynomially parameterized sets, actually. Okay, so as I said, bounding sets of ill-posed inputs is an application of covering number, and the set of ill-posed inputs is often an algebraic variety. So back to the inverting a matrix case, determinant equals 0 is a polynomial equation in the entries of the matrix, so that it would fit it. We'd be talking about a real algebraic variety for V there. A class of examples that I'm very interested in are low-rank tensors and tensor networks. These would fall into this second category of images of real polynomial maps. So if I look at the set of low-rank tensors or low-rank tensor networks, then the low-rank decomposition is actually a polynomial parameterization of that set. So that would be here. So covering number will let us say things about dimension reduction for low-rank tensors. And actually also neural networks can also fit into this framework in a kind of a less obvious way, which I hope to come to at the end of the talk. So we can even say things about neural networks with non-polynomial activation functions. So say ReLU or in principle sigmoid as well. So maybe but going through a polynomial description or polynomial approximation. Okay, let's get into the main theoretical contribution first. Okay, so this is going to be a table just to situate our contribution in the literature on covering numbers. So covering numbers of sets is our somewhat classic topic in geometry and metric geometry. So there are previous results. Let me tell you some of them. So here I'm in the setting where I start with the set U in either R to the N or C to the N. Okay, so this field F is R or C. And U will either be a zero set of polynomial equations or have a polynomial parameterization, or I also actually allow polynomial inequalities, so called semialgebraic sets. Um, let's let Fi be all the polynomials participating in the description of U. So these FIs are not unique. I mean, there's going to be multiple possible descriptions of U, but let me just fix such a description, and these are my polynomials. And suppose that D here is a uniform degree bound on all the polynomials involved. Let's say the intrinsic dimension of U is little n, which is much less than the ambient dimension capital N. So I'm interested in this case where U is has much small the intrinsic dimension of my set is much smaller than the ambient dimension. Okay, these are the results, the prior results on covering number. Um, so I need to talk about covering number. I need to reduce to a bounded set. So I can take my set U and intersect it with the unit ball. Okay, that's just adding like another polynomial inequality that the norm of my vector is less than norm squared is less than or equal to 1. So my set V that for which I speak about covering numbers is this U intersected with the unit ball. Um, and I'm reporting in this rightmost column upper bounds on the logarithm of the covering number. Results are often stated in terms of this log of the covering number, which is also known as the metric entropy. Okay, so there's results in different settings. For example, the semi-algebraic setting, and the result is stated in terms of the ambient dimension n and the number of constraints. There are, also results in kind of with some assumptions in the variety case, on the zero set of polynomial case, but with some assumptions on the variety. So this here we're assuming that actually it doesn't have singularities and it's a complete intersection, which is to say that each equation here is algebraically independent. And actually this here is the more general result. But what I want to highlight, the details of this slide aren't particularly crucial, but I want to highlight that all these results have kind of a leading term that's looking like this. The intrinsic dimension, little n, times log of 1 over epsilon. Okay, this term is actually easy to understand because this is if V were to be so if U were to be a little n dimensional linear space and I intersect with the unit ball to get V, then and I try to cover this kind of linear space intersected with a unit ball with epsilon balls, then each epsilon ball has volume epsilon to the little n in the linear space. And so I should expect on the order of epsilon to the minus n, little n balls needed to cover. So, and that's what this is saying. So this term is corresponding to the case where where you would just be linear. Um, these other terms are actually capturing the nonlinearity of U. Okay, the fact that it's not actually just a linear space. And the crucial thing I want to stress here is all these prior results have a linear dependence on the ambient dimension, capital N. Um, okay, so this is quite undesirable. because we're in the setting where we're supposing that capital N is much more than little n. So, okay. Here are contributions in this setting. So we can say give a covering number result for semi-algebraic sets with inequalities, for zero sets of equations, and also for polynomial images. We're making the most progress actually in this bottom row. So in the bottom row where V has a polynomial parameterization, then we actually do not have the linear dependence on capital N, just a logarithmic dependence. So this is actually this bottom row is kind of a big improvement for polynomial images. The others, this variety case, we're actually just matching what was previously known, but by a different argument. And then the semi-algebraic case, there's kind of a moderate improvement. But this bottom row is where the conclusion is strongest. Okay. I do want to give a hint of the proof because it is quite straightforward. And in particular, it seems to Yifan and me, it's quite a bit simpler than what was in the literature. So our proof is using a slicing argument, and it actually gives us an upper bound on the covering number for a bigger class of sets than just algebraic varieties. So it could be used more broadly. So I'm going to tell you this bigger class of sets, but first let me remind you that um, if you look at the set of affine planes in Rn with the same dimension, then there's a unique up to scale measure on the set of affine planes that is invariant to translations and rotations. Okay, so um, so we'll say that a class set that a set V in Rn is Kn regular. This is our definition. Our This is basically the class of sets for which our proof works, Kn regular, if there's two conditions here. So for almost all affine planes L, and the almost all is with respect to this measure that's invariant to rigid body transformation. So for almost all affine planes L that are too small, um, so their codimension is strictly more than little n, then V intersect L is empty. So if I try to intersect V with an affine plane whose dimension is too small, then actually almost surely the intersection is empty. And for all this is the second condition is for almost all affine planes that are not too small, their codimension is less than or equal to n. Then V intersect L has at most k connected components. Um, so if the set V has these two conditions, I call it Kn regular. It turns out that algebraic varieties, polynomial images, semi-algebraic sets, they're all actually regular sets with explicit bounds on K and N in terms of the degree of the polynomials in their description. Let me show pictures to explain what's going on in this definition. So suppose that V is this curve here in R3. So this is the twisted cubic, and it's a polynomial image of the map t goes to t squared, t cubed. I claim that this is regular with this is Kn regular with k equal to 3 and n equal to 1. So um, let's just see what it means. So this first bullet means that for almost all affine planes of codimension strictly more than 1, the intersect L is empty. So an affine plane of codimension strictly more than 1 here would be a line or a point. So for almost all lines or points in R3, the intersection with this curve is indeed empty. That's the first bullet. And the second bullet, for almost all affine planes of codimension less than or equal to 1, V intersect L has at most k components. So codimension less than or equal to 1, this is a plane or the entire 3 space. So clearly, if I intersect with the 3 space, I get 1 connected component here, but if I intersect with almost any plane, I get at most 3 components. And this is here coming from the fact that this parameterization is a degree given by degree 3 polynomials. So this is also k, the regular condition, the second bullet with k equals 3 does actually hold here. So that's what this definition is saying. You should think that n is the intrinsic dimension here. And k is kind of capturing how nonlinear it is. When I intersect with linear space, affine spaces, how many connected components can I have? So that's intrinsic dimension and kind of some crude measure of nonlinearity here. Okay. Questions at this point? I'm happy to take questions if there are any. Okay. So the to show that the algebraic sets, varieties and polynomial images are actually Kn regular, there's a simple hammer that we use called the Milnor-Thom theorem. And this is a kind of a basic result in real algebraic geometry that was found almost concurrently by Milnor and Thom in separate single-authored papers. And I'm just showing you here the first page of Milner's paper, and it's a fairly short paper that both of them wrote. Here's so the setting for so what does Milnor-Thom say? If we have a variety, a zero set of p polynomial equations and here m unknowns, then if we assume a uniform degree bound here of k, then the sum of the Betti numbers of the zero set V is at most this. So this degree k times 2k minus 1 to the power of m minus 1, where m is the number of variables. So notably, p, the number of equations, does not show up in this bound, and it's just in terms of the degree bound and the number of variables. And actually, we're also getting a bound on the sum of all the Betti numbers. But in particular, Betti 0 is in there. So that's the number of connected components. So this is also a bound on connected components, which is all we need. So this is the hammer, and it lets us show that all our algebraic sets are Kn regular, that they interact nicely with affine spaces. Okay, here's the main result, our main theoretical result. We let V be a Kn regular set in R capital N, and we suppose that it's inside a box whose axes are parallel to the standard basis vectors. It's inside a box whose side length is 2t. Okay, then if I consider covering with epsilon balls, where epsilon is less than the diameter of V. So this is the non-trivial range of epsilon. Beyond this, I'm just covering with like one ball. So I try to cover with epsilon balls, then here's I give you this upper bound on the metric entropy, the log of the covering number. Let's just look at the second line. So I have little n, my intrinsic dimension, times log t over epsilon. This is the term we always see, like as if the space were linear. And then we have this as the correction term for the nonlinear aspects of the set. And it's on the order of intrinsic dimension little n times log of ambient dimension plus log of k. So we then, when we get explicit bounds on little n and capital K for different algebraic sets, we can plug them in and then get results for varieties and polynomial images, so on and so forth. A nice thing here is that a priori we're just seeing a log of the ambient dimension. And the way that the ambient dimension might survive is through K here. But if we can get kind of reasonable control on K, we'll end up just with a logarithmic dependence on the ambient dimension. Okay, here's a, a hint on the proof. So the proof is by induction on little n, effectively. So supposing our set V is this surface, this blue surface on the right, it's inside the box like we assumed. Um, what we're going to do is lay down a grid of planes in R3, parallel to the standard basis vector planes. Um, and this will cut up V. So suppose this here is one cell in this grid of planes. I now will inspect each face of this cell. So that's what's going on in the left of this picture. This is one face. And I draw also a grid now of lines in this two-dimensional face. Um, uh, okay, and each grid line will intersect V at some points. So here, this particular grid line is intersecting at these 3 points. What I will do, so I'm going to construct a covering of the original set V, but kind of starting from these lower dimensions and going up. So I take a ball centered at each of these red intersection points with a radius big enough that it will contain all parts of the intersection in adjacent cells to this intersection point. So I just take a ball. I take a ball that will cover this cell and this cell. Um, and I do this for each red intersection point and also for each grid line. Now this will ensure that we cover this what's depicted here in blue, but there could also be components here that are completely contained in one cell and missed. But we then get actually a control in the number of such components. That's coming through K, where we in the Kn regular set definition. So we also will put a ball of radius epsilon to cover each component that's completely within one cell, but then there's a control in the number of such components. That's the basic idea. So we would cover this face and build up a covering to the entire set V. One gets kind of a recursive count on the number of epsilon balls needed here, and this is the idea of the proof. Okay, so. Yeah, so I just want to stress that it's sort of a simple idea of cutting up the set V all the way down to a curve, um, and using the fact that by our setup, the set V intersects with affine planes in a nice controlled way. So we're working with regular sets. Okay, let me just report to you a immediate corollary. So like I said earlier, bounds on the covering number give us bounds on the tubular volume. So suppose that yeah, so that's what's being worked out here. If xi are centers in V, where balls of radius epsilon cover V, then if I increase the radius of the balls to 2 epsilon, then I get a covering of the epsilon tubular neighborhood of V. So the epsilon tubular neighborhood of V is then contained in the union of these balls of radius 2 epsilon. So bounds and then the volume of the tubular neighborhood is the number of balls times the volume of one ball of radius 2 epsilon. So in this way, bounds on the covering number give bounds on the tubular neighborhood volume. We kind of flesh this out in this corollary, but I want to skip over this for time purposes. Okay, that was the theory part, and I'll now go into the applications to data science. Are there any questions at this stage? Okay. Okay, so I hope to get to three applications. The first is going to be a pretty immediate use of the theorem to low-rank CP tensors. Okay, so if you haven't seen them before, I think of a tensor here as just an array of numbers, a D-way array, generalizing a matrix, and in the first mode, the tensor has a dimension of n1 and then n2 up to nd. So this is a visualization of a tensor here, three-way tensor. So one can find tensors in a number of settings and applications. Some data is just naturally organized in tensor format rather than vector or matrix format. For example, categorical data, where there's three kind of features, three properties describing each category or more. Video stream or 3D images would obviously be naturally encoded as a tensor if we want to preserve spatial proximity in our representation of the data. Also, moments of multivariate data sets. So if I look at the covariance matrix of data, I get a matrix, but I could also look at D-way correlations of data. And this gives actually D-way tensors. Another way of getting tensors is by just having a multivariate function, scalar valued, and looking at all of its partial derivatives at a point. This generalizes the Hessian matrix and also gives you a tensor of derivatives. Okay, so in all these cases, the salient feature for tensors is that they can be very, very large, particularly when this order D is big. So if there's D modes here, each having, say, n subdivides, then our tensor is n to the D sized. And in a lot of settings, compression quickly becomes important just to be able to store this thing, do anything with it. This one of the simplest ways to compress a tensor is through the canonical polyadic decomposition or CP decomposition. And this is you can think of this as one of a few different possible generalizations of low rank matrix factorization. I'm showing you a visualization of CP decomposition here. So on the left, there's some tensor that we start with, and this should be an approximate symbol here. So we'd like to approximate it as a sum of outer products of D tuples of vectors. So this is it symbolically. I'd like to approximate X as a sum of outer products of vectors. This thing here, this outer product of vectors, so AI, BI, and CI would just be n-dimensional vectors. And this all together, this outer product is in here, it would be an n by n by n tensor. And its entries are given by the three-way products of the entries of A, B, C. Okay, so just like an outer product of a vector with another vector, but now say with d vectors. So the thing to note is that in such a decomposition, on the left-hand side there would be n cubed entries, and on the right-hand side there are just three Rn parameters. So we have here R such outer products, and each one is consisting of three n-dimensional vectors. So if R is small compared to n squared, then this is a compression. Um, Now we're usually interested, like I said, when there's an approximation here, but the CP rank is it's the smallest number of rank one terms that are needed to exactly sum up to the tensor. So if I actually did insist for there to be an exact equality, with the smallest number of outer products, then that smallest number of outer products R is the CP rank. Okay, and it's always a finite number. Um, so, you know, low rank decompositions of tensors are studied and used in lots of contexts. But I want to ask the question here, how powerful is what approximation power does this set of low rank tensors have? Okay, so I'll formalize this by asking if I take a random tensor, say say with Gaussian IID entries, how close should it be to being low rank? Does a random tensor look low rank? Um, um, or is it very far from low rank? How expressive is the set of low rank tensors? So this is a question ultimately about the volume of the tubular neighborhood of low rank CP tensors. So I will tackle it by working out the covering number of CP tensors. So I let V here be the in Rn up to N1 up to ND be the set of tensors with CP rank at most little r. Um, then here's my bound on the metric entropy of rank R CP tensors. It's being expressed here in terms of this quantity n bar, which is just the average of the n's. So if these are all the same, n bar is equal to n. We get an improvement in this quantity, in this upper bound. So there's a term that we can subtract off in the case when the rank R is really small. So if R is less than or equal to the minimum of the ni's, this is the so-called undercomplete case in the tensor literature, then we get this improvement in the bound. Otherwise, it looks the same. Um, okay. Yeah, the specifics of those formulas aren't so important, so I'll just proceed with the conclusion. Um, so let's suppose we're asking how close is a random tensor to low rank. So let's let T be a random tensor with IID standard normal entries. Let's say that capital N is the number of entries. And I want to just this is this is just saying I'm not in a trivial setting, so I want to say that capital N is at least 8. So I genuinely I at least have a 2 by 2 by 2 tensor. Um, Let me look at the event that my random Gaussian tensor T is within an angle in radians of epsilon to some rank R tensor T prime. It's helpful to talk about angles here because rank of tensors is invariant under non-zero scaling. So this is kind of the most appropriate distance, I claim. Um, so then in this, I report the result here in the undercomplete case when the rank is less than or equal to the minimum of the ni's, and epsilon here, this angle is less than 30 degrees, then the probability um, of the event happening, of the random tensor being within 30 degrees of a rank R tensor, has this upper bound. Okay, so some formula here. And this comes from plugging in our covering number result to the tubular neighborhood volume corollary. Okay, let's just unpack it and plug in some numbers to see what it says. So here's the numerical reference. If I look at three-way tensors, and I take all the mode dimensions to be 100, so 100 by 100 by 100 tensors, and I think about rank 30 tensors. These constants here in this bound, you can take them to be 3 by looking at the proof. Then the probability that my Gaussian tensor is within pi over 6 radians is really small. If you plug all this in, it's less than it's about e to the minus 40,000. If I look at the event that my Gaussian tensor is within pi over 7 radians of rank 30, then actually this probability drops to e to the minus 140,000. So really, really astronomically small. Um, so yeah, our so this I was surprised that the numbers came out to be this small, to be honest. And so the conclusion here is that sort of a structureless random tensor is actually going to be really far from low rank. The chances that it's well approximated by low rank are astronomically small. So the I interpret it as saying that low rank approximation is going to be useful for tensors when there is some structure in your problem. That the tensor you're dealing with is not thought of. It's not useful to think of it as just a random Gaussian tensor when there's some underlying structure there. Okay. Questions on this application?
Hi, so this is also holds for matrices, right? So same thing for d equals 2.
Yes. Yeah. This gets you a result for matrices. It might not sure if it's optimal for matrices, but that's right.
Yeah, was it known for matrices? Sounds like something should. Yeah,
I
okay.
believe it was known. Yeah.
Mhm.
I don't have a reference offhand. Thank you for that. Okay. Let's proceed. Application 2. So this is about randomized polynomial optimization. So suppose we look at a nonlinear least squares problem. So P here is a map from R little n to R capital N. And so just to fit in with the setting of this talk, I'll suppose that P is a polynomial map. So these are like residual functions, the coordinates of P. I'd like them all to be 0. So I want to solve the equation essentially that P of x equals to 0. But there's noise in my problem, so I set this up as minimizing the L2 norm squared of P of x. And I'm interested in this when actually the number of equations, capital N, is much more than little n. So a very overdetermined polynomial least squares problem. So and the goal of this application is to reduce this the computational burden of this problem by passing to a problem of smaller size that still gives a good solution to the original problem. So I'd like to make numerical optimization for this problem easier, such as gradient evaluations or quasi-Newton methods, make them cheaper. So the basic idea here is sketching. So I want to replace this minimization of P of x by a minimization of S times P of x, where S is a short fat matrix, M by N. And so the benefit here is that if I were to say pre-compute S times P, then now I'm just working with M equations or residuals rather than capital N. And so if I can take M to be substantially smaller than little n, this should accelerate gradient evaluations and numerical optimization. Okay, so the question is how small I can make M so that these problems are well related to each other. And the covering number gives us a way of controlling little m. So here's the conclusion. The way that the covering number gives this implication goes through Gaussian width, but I'll suppress this implication. This is the conclusion here, that if P is a polynomial map and the functions here are degree at most D, then so then for any epsilon delta between 0 and 1 with a failure probability of delta, I can get this approximation for all x, that P of x and S of P of x suitably scaled are within 1 plus or minus epsilon of each other, provided that M is at least this big. So N here, so this is my number of variables. This is some logarithmic term. And then I have my log of 1 over delta here. But this, is quite comparable to little n. So this could be a substantial improvement over capital N. Okay. Let me skip over this. This is ongoing work. Still ongoing. Essentially out of time, but is it okay if I take another 3 minutes or so, or is that okay?
Yeah, I think you can.
Absolutely.
Yeah.
Okay. Yeah, so this is the application to neural networks. So just a quick reminder on the setup of statistical learning theory. Suppose we have data that's sampled from some distribution, data x comma y. In statistical learning theory, we have a hypothesis class F for how the data x and y might be related, and we train over samples from the distribution xi, yi. We have little n samples. And one does the training by minimizing some risk over the samples. And it's empirical risk because there's only finitely many samples. So we want to minimize the average of the loss between hypothesis of xi and yi. Now, this is what we do in practice because we only have finite data, but we'd like to, in statistical learning theory, minimize the expected loss over the distribution. This is really what we would hope in this theoretical setting to minimize. The generalization error is the worst possible gap between these two losses. So the max over the soup over the hypothesis class of the expected loss minus minus the empirical risk, the population risk minus the empirical risk. So we'd like this to be small because then we know that we didn't lose much by just working with finite amounts of data. And the set of hypotheses is often nowadays a set of neural networks with a given architecture. Okay, so this is how I'm thinking about a neural network. Just composition of functions. Okay, I'm in here as in a fully connected feed forward setting. And once we fix this architecture, as we vary the parameters of the network, say weights and biases, we get a class of functions. This gives us F, where the class of functions could map xi to y. There's a relation here between covering number and generalization error. So this worst possible gap. This is the relation So basically, this is called Dudley's integral, this quantity here. So this is the integral of the square root of the metric entropy as we're integrating over the radius epsilon from 0 to infinity. And this, with another term, gives an upper bound on the generalization error. We're looking here at covering number of which set? So it's of this set. A set of n tuples where n is the number of data points of the loss between f of xi and yi. This is like the n tuples of possible losses as you go over the hypothesis class. So the covering number of that set is comes up, the bound the generalization error. And so using our covering number result, we can obtain upper bounds on generalization errors of neural networks. We can do this actually when the activation functions are rational functions, so that is ratios of two polynomials, or when they're ReLU, which is piecewise linear. And as far as we can tell, the generalization error bounds that we get are comparable to existing bounds from the machine learning literature, but through a very different proof technique. Okay, so I'm out of time, but this is a sample result. So this is the setting of a rational neural network. So not used too much in practice, but there have been some papers where you take an activation function that's a ratio of two polynomials. You can approximate other functions as rational functions, like ReLU or sigmoid. And if you have a depth L with D fully connected feed-forward network, we let the degrees on the rational function numerator and denominator be upper bounded by S. Then we get some bound on upper bound on the generalization error expressed in terms of L and the width or the depth and the width here. Okay, so you also, so here the point is that we're assuming the last layer is one Lipschitz. So up until the last layer, we have a composition of rational functions. So and then we follow the last layer is one Lipschitz. So Lipschitz maps functions don't change covering numbers. I mean, one Lipschitz doesn't change covering number. So we can we can look at apply our result with the polynomial parameterization, basically after clearing denominators in the rational function activations to control the covering number of the network up to the last layer, and then just use Lipschitzness. For ReLU, our idea is to approximate ReLU by rational functions, and there's results on kind of the approximation quality of ReLU by rational functions that we can use. So we also have a version of this result with ReLU activations. Okay, that's it. So the conclusions, what are covering numbers? They're just a basic notion to measure the size of a set in a metric space. For sets defined by polynomials, you can use regularity properties, namely the Milnor-Tom theorem, to control this covering number. And there's implications in data science and applied math to tensors, randomized optimization, statistical learning theory, and others, I think. Okay, thanks a lot.
Wonderful. Thanks, Joe. Appreciate that. I'll open up for any questions that anybody listening has.